Okay. Yeah, welcome to lecture for the two people in the game.
No, it's super hype.
No,
Everyone's
no.
here.
Well, I think we did a bad job of announcing this one. If you guys aren't watching this, the schedule of stuff we posted is final, so so it is good to I don't know, put that into your calendars somehow. But yeah, anyways, today's lecture we're talking about neural networks, backprop, and then CNNs. This hopefully is a familiar topic, or at least you've heard of it. Very popular, and we'll be getting right into it. So, obligatory joke is this is basically C-147 in a lecture. So, if you do want like a more mathematical formal education, like this sort of track of like M146, C-147, if you're interested in anything we say today, this will definitely be like the sort of class for you guys. So, yeah. Anyways, so we start off with neural networks. So neural networks are composed of neurons. So neurons were sort of inspired from the brain, like the biological brain, because the biological neuron is like this one unit that's very sort of like regularized. It occurs like, is it billions or millions? Many times in the brain, and it exists pretty much similar, identical to pretty much every other neuron. But it's the connections and the weights on those connections and stuff like that that makes neurons be able to do really complex processing tasks that, basically our brain's very complicated. So we sort of drew inspiration from this and we were like, okay, what if we created well, technically they are all called artificial neural networks, but basically like an artificial neuron, some mathematical unit to represent these biological neurons. So we talked earlier about logistic regression. Each neuron technically can be thought of as behaving as a individual unit of like a logistic regression. So this is what a mathematical neuron looks like. Hopefully you guys have seen something like this before, but essentially what happens is we have n inputs, and then we have n weights that correspond to those inputs. We multiply each, like, I suppose you could think of each of these 1 to n things as dimensions. We multiply each of those along its dimensions with the corresponding weight. We sum them together with a bias, and then we pass it into an activation function, which we'll be talking about later. And then finally, we get the output of the neuron. This is basically the fundamental building block of a neuron. More strictly speaking, so this is what we've talked about. More strictly speaking, for each neuron, it's essentially what we call like an affine approximation, or like an affine function, where we multiply each of the elements of x, if we think of it as a vector. If we multiply each of the elements x by its weight and then add a bias, that's an affine function. So z, in the future, z will be how we're determining, or how we're labeling this affine approximation. And yeah, basically this slide details some of the math. As before, what we can do is we can actually append the 1 to the x vector like we did in the first machine learning lab you guys had. And then we can put the bias in with the weights. That way we get z to just be the product, or the, in this case the dot product, but when we generalize to matrices and stuff like that. But in this case, the dot product between the x vector and the weight vector, including the bias term. So, I mentioned briefly the activation function. Let's talk about it a little bit. So an activation function introduces non-linearity into the system. This is like a really important concept, but we'll discuss it a little bit later. Here are 2 examples of activation functions you may have seen. The sigmoid one, because this is what we're using for logistic regression. So basically, we took that affine function result, and then we pass it into this activation function. So this is like an important step for all the neurons inside of your neural network, and the activation function is one of the hyperparameters that we can choose to describe our neural network. In terms of like just some more mathematical notation, again we have z being the result of the affine function, and then we pass z into, let's say, the sigmoid function, which we can denote with sigma. We just apply the sigmoid function onto z, and then that's the result of the neuron. So pretty simple building block, but the trick or the details lie in the implementation. So here are some common activation functions. If you want to like learn more about these, there's tons of active research and lots of rationale between why you use some of these. For us and for most things you'll be doing, like I suppose at the undergraduate level, most neural networks will use this function, the ReLU function. It stands for rectified linear unit, and it essentially says whatever you pass into it, if it's below 0, we have it as 0, and then we anything that's above 0, it behaves linearly. You can see how there's like a non-linear, non-differentiable point at the origin here. Again, we talked about how introducing non-linearity into the system is important. So ReLU will do the job. These other ones, leaky ReLU, ReLU, I suppose. Sorry, I'm butchering that pronunciation. I think most people say ReLU. Leaky ReLU is basically you can add a multiplier to the to essentially the slope of the negative portion of this plane. It's essentially to make sure that there's no like loss of signal occurring in the left, because essentially when you're making this 0, you're ignoring whatever you're passing in, which you might intuitively think would be better than ReLU, but I think algorithmically or like empirically it has been shown that ReLU actually performs better than leaky ReLU, which you might find as a surprise, but I don't know, empirical results are often hard to explain conceptually. Sigmoid you've seen before, and tanh is essentially, you can think of it as sigmoid, but one of the important things about tanh, and why tanh is actually preferred over sigmoid if you're going to use a function of this shape, is tanh is centered on 0, which is somewhat useful because you're able to have positive and negative values. Again, there's a lot of like, I don't know, like complicated stuff on why that might be important, but we're not going to delve too deep into that. Any questions from you guys about like this stuff? Okay, so we talked about individual neurons, but basically a neural network is composed of many neurons, which you might expect. So networks, like the next level of abstraction from a neuron is a layer of neurons. So a layer of neurons is basically this vertical column. Here we're looking at 2 layers. So most often type of neural network architecture is a fully connected layer, which is essentially saying that each of these neurons will map to every neuron in the next layer. You can see why this would be called a fully connected layer. So we don't show the inputs into this one, but you can imagine that this network is essentially like connected everywhere. This is important for learning because neural networks will learn optimally when everything is fully connected. This is like a sort of ideal scenario. We'll talk more about like, I think next lecture we'll talk more about like how this deals with like overfitting and stuff like that. But for now, fully connected neural network layers, you guys will be using these when you do your next lab. So, some terminology. First layer, we call the input layer. Hopefully this is evident why. Middle layers, they're called the hidden layers. Hopefully this is also evident why. Because what you're receiving is the output. The output is something that we've sort of brushed on. We've talked about softmax probability. I think if your guys' checkoff question for lab 2 had to do with how do you extend logistic regression to a multi-class classification task, you would use the softmax function. The softmax function basically accepts a series of inputs and then outputs like the probability that it is of a certain class. It's very fundamental for classification tasks, and often it is the activation function, or quote-unquote activation function. We just call it like the output layer. The output layer goes through a softmax basically as a classification thing, because most networks are trying to classify something. Any questions about that? Okay, another term. So the process of inputting something into the network and passing it through forward till you get to your output, we call this forward propagation. When you take something that is trained, like a network that is trained, and then you do a prediction by passing some sort of new test input and then getting the result. You're using forward propagation to do inference, which is just some terminology to throw at you guys. So we'll run through a quick example here. Well, I guess there's only 2 of you guys, so you guys are somewhat pressured to answer. So if 5 and -4 are the inputs to my neural network, right? Let's say we're talking about this neuron. What value would this neuron have if these were the weights and this was the bias? It's just mental math check, really.
1?
Yeah, 1. That makes sense. Okay. I think historically we ran through all of these, but the idea essentially is 5 plus 5 times 1 plus negative 4 times 2 plus 4 is equal to 1. This is how the forward propagation path works. We're not actually talking about the activation function in this case, but if you go through the rest of, well, here are the rest of the answers because hopefully the point is evident. But yeah, this is not necessarily talking about the activation function yet. So, as a question, what is a way that we might be able to like represent these operations? Like, what is something that we often work with to represent like this sort of, I don't know, like math?
Matrix multiplications?
Yes, matrix vector multiplication, linear algebra, basically. It's a fundamental part of this. So here's some notation. It might get a little ugly, and we'll come back to this slide of it. But basically, what the notation is saying is that anything that's, I suppose its main letter is A, it refers to the output of the neuron after it's gone through the activation function. Any superscripts refer to what layer it is in. I'll go into detail about this more later. The Z is what we were talking about earlier. This is the result of the affine function. This is basically the output before going through the activation function. These are all vectors, by the way. And then the weights, this is not a vector, this is an individual unit. Basically, we like to store the weights in a matrix because it makes sense. Basically, all the weights from this neuron going to all the other neurons in the other layer. And then the weights for a layer will include that mapping for every neuron in the current layer. So the way we have the abbreviation, or sorry, not the abbreviation, the way we have the layer notation here is that whatever L is, this is the weight matrix between the previous layer and the current layer. I'll clarify that when we move on to our next example. So, W2. W2 is the matrix of the weights. So since we're looking at the second layer, based on what I said earlier, we're looking at the weights between basically the first layer and the second layer. So what do these weights consist of? I don't know. Do you just want to?
It's like the weights on the arrows, so it'd be like 1, 2, 3, -2, and -1, -1 in a shape that it would be 2 by 3.
The shape, I didn't give too many space or shape specifications because it's sort of up to how you up to how you want to define your matrix multiplications. But yeah, the gist of what you said is right. Here we do have it as a 2 by 3, but it is based on what's going to this neuron is in one row. So 1, 3, -1. But yeah. Anyways, next one, A1. This is before we go to the activation, or sorry, after we go to the activation functions. Except in this case, it won't actually matter, as you will see. But I'll just go through this. It's 1, 0, and 1, right? Because it's the first layer. And then Z2, it's just referring to these because it's the second layer. So I'll just speed through this real quick. It depends on how you want to define your matrix multiplication, but remember, 2 by 3 matrix multiply. We want a 3 by 2 multiplication. Wait, did I get that right? Sorry, 3 by 1, that's what I meant to say. Okay, 2 by 3 needs to be multiplied by 3 by 1. So the way we've defined our matrix space is such that W is going before A. So yeah, looks like that. This is generalizable. So basically, this is going to be our like sort of key equation for how forward propagation works. It's basically going to be that the output of the affine function is equal to the weights. The activations results from the previous layer plus the biases. This is again what we've been saying with the affine function, just formalized to being a vector instead of just scalars. And then A, referring to the activation functions, basically we pass Z into the activation function. This making sense so far? So now we go to backprop. So backpropagation is basically referring to, well, it's not actually strictly referring to a learning process, but we like to think of it as a learning process, where essentially we need to ask ourselves the question of how do we actually train our model? That's a very important question because you want your model to learn. This is the point of machine learning, right? So we've learned all the setup for a neural network and running a prediction with it, but now how do we make it learn? How do we make it better? So, if you don't know, this is Prem, our pocket racers lead for last year. He's unbelievably based. And here Prem is suggesting, what if, first step we might want to do is initialize our network, right? What if we just pick random numbers to initialize our network? We were doing something like that in the machine learning lab, where we were initializing to random numbers. Ugh, look at him look. Okay, so he's not strictly wrong for saying that. Our initial weights and biases will be random, sort of. There's a lot of heuristics and research onto what you should actually initialize your neural network weights and biases are, because it actually somewhat matters in the training process. It can help a lot. I believe it is useful to initialize them to a Gaussian, but you can definitely learn a lot more about this. So yeah, the naive answer is yes, you could just pick random. But it may not be as efficient as some of the more complicated stuff, which you can learn about here. Okay, so we talked about loss functions in our first ML lecture. This is going to come back again, because we need to talk about how well our model is doing, and then be able to learn from it, right? So this is basically going to be where we start getting into what is called backpropagation. So a trained neural network, as in like you have trained it and it is doing well, it should be minimizing the cost function, because high loss, high cost is a bad thing, so we want to minimize it. This is again in theme with what, or like in tandem with what we were learning from the first ML lecture. So let's just talk about this example real quick, right? So let's say that our neural network looked like this, including all the outputs and neurons and stuff like that, right? Let's say that we inferred 0.9, right? But then the true value of what we were training on was actually 2.7. So we want to get to 2.7. What can we change in this network to get closer to 2.7? Like what values are we tuning pretty much?
The weights and biases?
Yeah. So it's pretty much the only things we can change, right? So let's just talk about weights for a second, right? Okay, we need the number to be more positive. So wouldn't it make sense to, for this 0.9 to increase the weight that's going to it, to increase the weight that's going to this one? And then in this case, this is 0, so it's like not actually contributing anything. But essentially what we want to do is we want to increase the weights to adjust for loss, right? We talked about this in machine learning. What is this process called? The process where we like step by step improve our model parameters while adjusting for like loss.
What keeps coming to my head is gradient descent.
Yeah.
Okay.
Gradient descent is what is being performed on the weights. So basically, okay, this is just some semantics about this particular example. But essentially, what we want to do is we want to say like, okay, it is sort of obvious how we might change these weights to change the final answer, right? But what about the weights before, right? It is still perhaps somewhat evident the previous layer, because we might be like, okay, this has a positive weight, so the ones going here should go up. But you can see how there's a layer of abstraction, right? There's something in the way. And then when you try to evaluate how you should change these weights and biases, and then if you wanted to go back again, it would be a mess. So we don't do it by thinking about it, like, what value should increase and what value should decrease. We have a formal sort of mathematical way of doing it. Okay, so this is just working through the example again, but you can see how this is becoming pretty complicated. Like, it's no longer intuitive what should be getting risen and what should be getting decreased. You might start to notice that what we're doing is, okay, these ones are immediately obvious, and then we move to these ones, and then we move to these ones. This is why this process is called backpropagation, because we're essentially propagating backwards through the network. Okay, any questions about that? All right. Guess we're not pausing. Okay, there's gonna be a lot of math coming up. If you don't get it, that's okay, because we're not going to ask you to implement all of this by hand, or like in NumPy, in your lab. But this will come back, definitely, if you were to ever go into this stuff or take a class. So, you know, do your best to follow along. If you guys have any questions, feel free to ask. But basically, let's revisit our notation, right? So we had A's denoting things after the activation function. So this is basically like, this is the neuron's affine function. This is just the weights times the input plus the bias. And then this is the activation function, which moves it to our notation, which is saying A. These are the weights, and then this is before the activation function, and this is basically this is basically our notation. We're gonna go pretty extensively into using the notation. So if you have any questions about it, be sure to ask. So before, when we were doing gradient descent, what we needed was a gradient. Basically, how the loss function would change when we changed our weights. That was basically what we were looking for. So we're gonna look for something similar again. So here I've written the partial derivative of the cost function, or if you'd like, the loss function, with respect to the affine output of this neuron here. So basically what this is saying is, if this input, if this affine output of this neuron changes a little, how does the cost function change? Well, this is pretty similar to something that we're looking for, right? Because we're sort of thinking like, okay, what values should I change around to make the cost function better or worse, which is, again, a gradient descent process. So here we're talking about the very last neuron. If you remember, we want to propagate backwards from this one. This one is often called like the upstream neuron. If you think of like down the stream as this way, or wait, did I get that right? Like the stream upstream is here and then downstream is here, basically. Okay, so I forgot to mention that we can just call like, cost function error, basically. So we want to find the error of the, we want to find how the error changes when we change every neuron, not just the very last neuron. So we're gonna exploit basically the derivative chain. This is, hopefully you guys are, somewhat acquainted with this idea. But essentially what we're doing is we're defining, not defining, but using intermediary variables to be able to say, hey, what is the change in the error with respect to the L-1 layer? Well, we can get there by saying how the change in this layer occurs with respect to the previous layer, and then use our previous gradient that we calculated here. So essentially what we're doing is we're coming up with like a process where we can move backwards, right? We calculate the derivative here, and then we move backwards, and then we need that gradient. Like, this is the term from the previous slide, how the cost function changed with respect to this later layer. We can use that in our next calculation, basically. So this is sort of what we're doing here, is we're deriving like a mathematical formal way to go back and change or understand how we need to change the weights in this layer to better understand or to sort of manipulate the loss to be lower, because we do want to minimize it. Is that making sense so far? Okay. So, because we had an activation function thrown in here, it's going to get a little bit messy, but let's say our activation function was indeed sigmoid. We have the we have A, which is the result of the sigmoid one. We have it as the sigmoid being applied. This way, when we talk about our derivatives with respect to loss, we also need to bear in mind that we need to include the partial derivatives with respect to A and then Z, because we do want to get to the weights at the end, right? So if you remember, like if we want to get to the weights, we need to go through Z, but Z is behind A, the activation function. That's essentially what we're saying here. So our intermediary variable chain is essentially getting longer. because we need to account for our activation function and all that stuff. So I think the next slide will go a little more in depth to that. Oh no, actually, this is just saying that we can move backwards like arbitrarily far, because this process is essentially robust. Like we can always use the upstream gradient to calculate the next one behind it, is essentially what we're saying here. We just need to apply the chain rule more and more. Okay, so this is what I was talking about earlier. Eventually the, oh sorry, this is not the thing I was talking about. Okay, this is the thing I was talking about. Eventually we wanted to get to the weights and biases, right? So here we are. The derivative, partial derivative of cost, or essentially the gradient, with respect to the weights and the biases of a particular layer, because these are the values we want to change, right? And you see that all we need to do is we just need to include the partial derivative with respect to z and the partial derivative with respect to w. Because again, we're just sort of repeatedly applying the chain rule to get the gradient that we want. This, as you recall from our machine learning, this is the gradient that we would use to update these particular weights. Because we could, again, do the thing where we subtract this and then the learning rate, and then if you remember like our parabola graph or mean squared error, and then we'd move in the direction towards like some local minima or something like that. This is how we essentially improve our network. This is like the most fundamental training process behind a neural network. Okay, and this is essentially pretty much just a summary. This is our affine approximation, and then these are how the weights, derivatives with respect to weights go, and then these are how the derivatives with respect to the biases go. So essentially what we're saying here is that whenever we take, essentially what we're saying here is that the partial derivative of the affine function with respect to the weights is always going to be the activations of the previous layer, because that's just how the vector calculus ends up working out. And then for the biases, it's 1, because, you know, the bias term is by itself. Okay, I wouldn't worry too much about this. This is essentially introducing a new variable to sort of vectorize like all of our gradients per neuron's affine function. This is essentially saying, you know, each layer of neurons is composed of many neurons, so we need a whole vector of these. Is this like making sense so far? Okay, so we can write the vectorized equations, which we've just included here. You can sort of look into them later to get an idea if the intuition is correct, but we don't demand like too much of an understanding of this. If you did want to go back and look, one thing that we should note is that this dot here, if you've never seen this before, sometimes, well, the annoying thing is it actually really depends on context, but here we're talking about the Hadamard product, which is essentially saying that we need to do an element-wise multiplication of two matrices. This is essentially saying that when we apply our, like all the gradients that we have in this delta, we need to do it element-wise and not matrix multiplication-wise, because that would mess stuff up. Okay, do you guys want a break? I know it's kind of a lot. This is the speed run of like what was essentially, I think in C147 this spans like maybe 4 hours or so, but the math is a lot more in depth. Okay, no takers for a break.
Okay, so now we're going to be talking about convolutional neural networks, or CNNs. So something that's a key part of what Justin said is that all the layers and all the neurons are like interconnected. They're all connected to each other, and sometimes our features are not always super connected to all the other features. So, like for an image, for example, like this nose, like the pixels in this nose aren't particularly related to the pixels in this eye. So it's not super helpful to consider them all as fully connected. Yeah, so we don't actually care about each and every pixel, and thinking about it as such would be a lot of inputs. And yes, we can make it faster if we have less of these. So, do you guys know what convolution is? So normally in convolution, you have a kernel like this, and then you place it over a matrix. And then what you would do is you multiply each element of the kernel by the element on top, it's on top of in the matrix. You do that for the whole kernel, and then you would add up those values, and you would have a new value, so that'd be 14. So yeah, it'd be 1 times 0, 1 times 0, etc., etc., and then you add up all of those, the zeros and the 4s and the 2s, and then you get 14. And so if we had like this matrix on top of here, and then we moved it over, and then moved it over here and here, so we'd have 4 different values. So usually in convolution, I think we talked about this earlier, you have the kernel and you'll flip it before you do all of this dragging and adding and multiplying and stuff. But for convolutional neural networks, we're actually not going to be flipping it, we're just going to be multiplying and adding. So it's not true convolution, but that's okay, we're just going to call it convolution. So images, do you remember, so usually for images we have like RGB, so we have like the red layer, you have the value for red, you have the value for green, and the value for blue. You also will have, so for each of these you're going to have like a kernel, and then for each colored layer it's a channel, and then the 3 kernels that you're going to be using is the filter, and then the convolution after is going to be your feature map. Yes. So I guess this is kind of an example of how the math works. So you have this kernel for here, and then you put it on top of the red channel, which is like what your image is on the red RGB scale. And then you'd also have a separate one for green and a separate one for blue. And then you'd be multiplying them and adding them, and then you'd be using this value to get the output. And so for example, if you have like a feature like the way this sorting curve is, yeah, let's like look at this sorting curve of a mouse. And then this would be the feature, this is the curve. And then if you look at it from like in terms of ones and things, you have like ones here and negative ones there. So if you were to multiply it, you'd have positive values where it matches this particular shape. Yeah, so if it matches, you'll get like a high number, and if it does not match, you'll get a low number. And so we're gonna keep doing this over and over essentially. So to go over everything, each layer has filters, and each filter has a distinct feature. And then after convolution, we'll have like a feature map of all of these. And then, yeah, each of the filter has a kernel, and then the kernel responds to a channel in the image. So after we get, so before we got like this output, which would be a layer, and then we would keep doing this for a lot of different features. So we have like the curve of the mouse, and then you have like the nose of the mouse, or whatever else features you see for the mouse or for the object you're looking for. And then you stack these layers together so that we'd be able to have like a 3D output. And then also, if you know, like, so let's say we wanted to have the same size, right, as we did before. So if we like apply the kernel to where the image starts here, this would be the center, and then it'd be applied here. But there wouldn't be a point where this would be the center. So something we can do to make that the center of where we're using our kernel is to add 0 padding around, so that we'd be applying this kernel here, and now this is the center. And then if we move it over to the center, and then every, essentially all of these values would have their own value here. Yeah, this is like how you would calculate such. So these are hyperparameters, so things that we can kind of adjust to make it better. So step size is like how much detail we want to notice from the original image. filter size, so how big the features that we're looking for are, the filter count, how big our out should be, and zero padding, so how many zeros we want to add around our input. Are there questions? Oh, okay. So now we're going to be talking about pooling. So we're talking about like when the model is too complex, and then so when our model is too complex, it often leads to overfitting, and we don't want to do this. So do you remember when we talked about like downscaling? So we make this into this. Do you remember this? So what we would do is like we're averaging the pixels in a window and then we're applying it there. So I guess if you look at here, this is like, if this is a kernel and then we're making it smaller. So something, yeah, so basically we're averaging in this way, so average pooling, we're like, it would end up making it be smaller. So if you actually apply it to like an image or something, so if you have an image that's like white on black, for example, if you were to like average this like section, between the white and the black, the average would be gray. So you get like a muddled image that would look more like this, which is not ideal. So yeah, and if we keep doing this over and over, so like eventually this like section would be gray and then it would get darker and darker, and then we kind of be losing our image entirely. So something we can do instead is, okay, this is called, spoiler, this is called max pooling. So what we're gonna do instead is we're gonna be taking the, like of a section, we're gonna be taking the max of it. So for this, for example, for this section, the max is 255, so we're gonna be taking that. Here's it's 0, here it's also 0, and here's 255, so we're taking that. As opposed to if we had done the average, it would be getting 128, 0, 0, and then 128. Yes, so this is called max pooling. It's not exactly convolution. It's kind of similar to thresholding because the high regions stay high and the low regions stay like pretty low. And so if we're applying max pooling, we're able to get an image that looks like this, which is a lot more defined and a lot more clear than before. So this is just like a summary, I guess, or like what we've done so far. So we use convolutional filters to get certain features of the image, and then we'll apply an activation function to introduce nonlinearity. Then we're going to be using max pooling to condense the data, and then keep doing this to get the necessary features that we want. And then, so we can use this as the input for our for the fully connected neural network that we're talking about with Justin. But also to do this, we have to flatten or convert our output from the convolutional layer or the pooling into a 1D vector, so 1D vector, so that it can be applied to do as such. Does that make sense? I think this is okay. Do you want to explain this one?
Oh, yeah, we are kind of nearing the end, huh? Okay. Is that me? No. Okay. So, basically, one of the reasons why we introduced all the convolution stuff that Hope is talking about in the first place is like, there isn't necessarily any meaning between us taking the original image, flattening it, and then passing it all into the neural network. We would like to get some of the image like locality and stuff like that represented first, which is why we do all the convolution stuff anyway, which is why convolutional networks are built to essentially deal with images. So basically, fully connected neural networks, artificial neural networks, which was what I was talking about at the start, they deal with numerical data most effectively. If you think about what was happening when we were talking about like feature maps essentially detecting features, what that's essentially saying is, hey, if there's a feature present, I'm going to have a high value. That's something that artificial neural network would have a greater understanding of than if we just took the original image and flattened it immediately. So this is why like we sort of go through this intuition. But essentially what this slide is referring to is that like we do need to eventually get to, at the end, like if we're doing a classification neural network, let's say we were trying to tell the difference between like a dog, a cat, and a bird, we do eventually need to get to an end where we get a prediction of like, is this a dog, cat, or a bird? This is where the artificial neural network comes in, because we pass in all the numerical data we got from the convolutional neural network, flattened, we pass it into the artificial neural network, and then that will produce the output. Right at the end, it'll go through a softmax function, and then it'll give us probabilities of which class that it might belong to. So basically, this is like the entire process of a convolutional neural network. Any questions about this? This is like a, does it like make sense, like why we don't just flatten the image and pass it into this? Like that's pretty much the most important part of a convolutional network, why that's important. Okay, that is about it for this lecture. So thank you two for coming. Shame on the rest of you guys for, actually it's definitely our fault because we didn't do a good job of announcing it. Yeah, that's it. Here are like, I don't know, you might need ones.